Okay, we are live from Willis College for BSides Meetup, the first of the year? Or the second?
No, it's not the first of the year. Yeah, it's the first of the year.
First of the year, okay. So my name's Leigh Gilbert. I'm from far east Newfoundland, and I'm in tonight to teach you about binary exploitation basics. A little about me, I'm an instructor at the Cyber Cossack School in Ukraine, teaching malware analysis and exploit development to Ukrainians to keep their country safe right now. I'm currently just finishing off my exploit development course with OffSec. I'm retired military. I was a tank commander and a reconnaissance patrol commander back in the day. And I'm now living on a remote island off of the coast of Newfoundland. I studied under Occupy the Web for years, and I've been programming assembly, Python, and C for about 5 years. And here's my LinkedIn if anyone wants it. Okay, so the BSides Meetup, this is normally a 3-day course I do. Within the time constraints we have tonight, I basically broke it down into 4 different binaries we're going to go over. So the first is going to be a binary game to overwrite variables on a stack. That's the start to exploit development and doing a buffer overflow. If you've ever heard of remote code execution happening in exploits, it all comes back to the buffer overflow. Now, there's multiple vulnerabilities within the C program language. What we're going to be covering tonight is stir copy. So stir copy function, basically, it will take user input and copy it into a buffer without doing any bounds checking. So without doing bounds checking, we can overwrite things outside of that buffer and take control of the instruction pointer. Once we take control of the instruction pointer, we own the server, we own whatever the program is. So we're going to break it down into 4 different binaries tonight. I know some people had some trouble with getting MX Linux set up, so we have 2 computers. I think you got yours set up as well. So we'll huddle around, we'll share, and we'll get through this. So the way we're going to do it, I'm going to do the demonstration of it, explain it, and then we'll take my computer and your computer, and we'll sort of huddle around and we'll go through them, okay? So the first thing we're going to do the binary game to overwrite variables on the stack. Then I'm going to take you into a vanilla buffer overflow. From there, we're going to bypass data execution prevention, and then we're going to bypass data execution prevention and ASLR at the same time. Okay, so I'll just get you guys to come over to your binaries here and open a terminal. And let me just bring up the draw IO for game. So the first thing you have to do is compile the binaries. Now, everyone should have downloaded the C programs. And here we, whoops, let me just get into my binaries folder. So we'll compile the binaries. Now, you can see here when we compile it with GCC, we have no stack protector, exec stack, and then the name of the program, and then the output. So what we're going to do is no stack protector gets rid of stack cookies. Exec stack allows us to execute things on the stack, because right now in 2026, of course, you still can't do that. But I want to teach you how to walk before we run. So as you can see, it compiled no trouble. So let me just switch over here. So now we're going to open up GDB, which is a binary editor and viewer.
Can you put back your screen again? Because you stopped sharing.
Stop sharing? How about now?
Oh. Black screen right now. It was on earlier. Oh, there we go.
We're good?
Yes, there we go.
Okay, so first we're going to disassemble the main function. And as you can see, this is assembly language. This is what I program in and where I live. So what we're going to see is this right here is stir copy. So this takes the user input, stir copy copies it into the buffer. Now the problem with stir copy, and there are a multitude of different functions that are vulnerable. The thing with stir copy, it doesn't do bounds checking. So what we will do we'll set a breakpoint at the stir copy here. And all this does is stop the program right at the stir copy before it copies anything into the buffer. And next, we're just going to run the program with an input of a bunch of A's. Let me just put this over here to the side. OK, so the next command is display 60 words of hex from the ESP. So the ESP, if you've done the pre-course, is the extended stack pointer. It sits on the very top of the stack. So what I'll do now is we'll hit print ESP. And you will see it's at F040. So we come over here to the side and have a look at the stack. And we see it's right here. So this right here is the stack pointer. This shows where the top of the stack is. So we print our base pointer, which is the bottom of the stack, and it's at 098. So the thing to remember when you're counting in hex, obviously we start at 0. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is our base pointer. So here's our stack pointer, here's our buffer, and here's our base pointer. To the right of the base pointer, always in binary exploitation, this is the return address. So when the program crashes, it automatically returns to the return address to exit. If we control this, we control where the instruction pointer is pointing, and then we can take over the whole system. We're not going to do that right yet. We'll do that in the next binary. But with this game, I want it to overwrite a variable on the stack. So as you can see, I have a variable Z, and it's at 08C. So C is 12 in hex. So we come over here, and right here, this is variable Z, which is set at 0. So what we want to do, we want to overwrite this variable. So let's hit next instruction. And then display 60 words from the ESP again. Now, do anyone see where those A's went on that buffer? Does anyone know what an A in hex is? 41.
Oh.
So what we have right here, this is the start of writing on the buffer. So now what we want to do, we want to overwrite this variable down here. So as you can see, we have quite a ways to go before we reach there. So we'll continue on the program, and it says, continuing, you suck, X is still 0. So what we'll do, we'll put in 50 this time. Now, if this was real exploit development, you would be doing it with Python scripts. And we'll get into a little Python scripting in 2 more scripts. So we already hit our breakpoint. So let's hit next instruction and display 60 words of hex from the ESP, from the stack pointer. So right here, here's our stack pointer right here. Let's have a look for our base pointer. Our base pointer is at right here. So this is our stack right here. This is the variable we're trying to overwrite right here. So as you can see, we still haven't overwritten it with 50 A's. So as you can see, continuing, you still suck, X is 0. So now we sort of know that 52 is going to overwrite it. And again, we'll display 60 words in hex. Now, this is right at the stir copy. So as you can see, nothing's been copied into our buffer yet. However, when we hit next instruction, stir copy is called. And we'll have a look again. And as you can see, all these 41s right here are right down to where our variable z was. And as you can see, 41s are overwriting the binary. So if we hit continue here, you can see you have completed this challenge. Z is overwritten with 4141. So now you've just learned how to overwrite something on a buffer. And this is going to be really important in the next lessons as we start taking control of the instruction pointer and taking control of the servers. So what we'll do now, we'll break into groups because we had some trouble with MX Linux. And we'll give you guys a chance to run through this yourself. So if you want to come out with me and you two work together, and then the rest of us can sort of split between us, and we'll do it that way. Okay, so let me just. All right, so if you want to jump in here. So basically it's just copy and paste as you go down through, but just make sure you're clicked on that and not the box itself. Copy it in, and then we'll and just work your way down through it. We just did that one, so the one just below. If you guys have any questions, I'm here. Okay, so it'll be game class for the. C'est à toi. The game class, this one right here. Okay. That's the draw IO. Okay, so the first thing you're going to need to do, what I do, I just put it half screen and half screen. Yeah. Okay, so you're going to have to compile your binary.
Okay. I'm pretty much still new, so I still need a bit of
It's all good.
Yeah. Thank you.
So just come here to the first one. You want to copy that. No, just double click on the inside. Copy the text. Yep. So this is just compiling the binary we're going to use. Okay. Perfect.
This
all right.
Yeah.
So let's move to the next next command. And this is just opening up our GDB and just double click in the center. Yeah.
That sure makes it easier.
Yeah.
Well, that's what I wanted to do. I wanted to make it plug and play for everyone so you can actually see what's happening. So now you're going to disassemble the main function. That is the hardest part. There's a little work here. Now you're going to look for stir copy, which is right here. Okay. And we're going to copy that address directly across from it. Yep. Now, what you're going to do is put a B and a star before that. A space. And then put that address in, and that just sets the breakpoint at your stir copy.
Okay.
How are we making out?
So stir copy this. Which one is the
okay, so the return address is right next to your base pointer. So the base pointer, let's grab this command. So the base pointer is A50.
And then the return address is to the right.
Right next to it. Okay. So your breakpoint's set. So now let's go to our next one here. And now we're just going to run the program with some A's. So So all this is doing is putting A's into the buffer. There you go. Okay, so just go to the next command, and it should be an examine display. So this is just going to show you 60 words of hex from the stack pointer. So there it is. Okay, so I just haul the second one up here. Let me do this. Oops.
Do you want me to minimize it? Okay.
Do it like this, and then haul this terminal. Oops. Like so. There we go. Okay, so now you've done that one. So just copy this one in, and this one's going to show print where the ESP is. So copy that one and then have a look for that address when it comes up.
So I found it. It's this one here, and then this must be the return address. This one here.
That's right. Yep.
So I ran x/wx with the return address.
Okay, just let me hear one sec. Something is off right there. Okay. So we'll jump down to this one here.
Okay.
So we're going to run it. Okay. Next instruction. Okay, so now if you hit print Z right there, P and Z, no symbol in context. Let's do display. Oops, I got a weird little thing put on it. Okay, there you go. All right, did you find them?
We're supposed to find where those are in there, or no?
Yeah, so like this one here, I can't see your, what's the last three?
It's the 080.
Okay, so just find 080 on the side. Your ESP is always, I'll show you now, your ESP is always this one right here. So you can see this number here matches up with that one.
Okay.
So this is your top left corner is always your ESP.
Okay.
And then what's that one there?
It's 0D8.
Can I get in between you guys just for 1 sec?
Yeah.
Actually, I'm gonna
If you
close
prefer,
this.
say that we could come there also, so that you don't have to walk all the way here. So
I could do it the exercise.
say the
I was in
word,
bed
yeah,
all
yeah.
last week sick, so I'll do it. 0D8. So here is your right here. So this is your base pointer right here. So we came over to 0D0. That's this one. So 0, 1, 2, 3 is here. 4, 5, 6, 7, 8 right here. Okay, so you understand how I got that?
No, could you?
Okay, so right here,
Yeah, it's
0D8.
Yeah.
So we find 0D0,
Okay. Yeah.
0, 1, 2, 3, 4, 5, 6, 7,
Okay,
8.
got it, yeah, okay.
That's 8. So here's your base pointer. This is your stack, and here's your stack pointer right here.
Okay.
So this is how the stack is set up right now, right there.
Okay, got it.
So
okay,
now,
yeah.
once we know this base pointer is right
Mhm.
here, this is your return address right here. So always to the right of the base pointer, that's the return address right there.
Okay.
So if we do X, WX, and then copy this address.
Is the,
You can
said
see
it's
to return to libc main,
Okay.
that's the return address. So now when we get into the buffer overflow, the whole thing is once you overwrite that return address, you
Okay.
gain control of the instruction pointer, and then you tell the computer what to do. You have full control. Okay?
Okay.
So now let's get back to
And you
here.
said that's called the base pointer. Does it always, right? Does it
That's the
always look
base
like
pointer?
that With a 0x followed by 0?
No, not all the time. No, but always to the right of it, that's always the return address. Base pointer, return address. Every time a stack is created. So now have a look for Z and see if you can do that one.
I don't think it's going now. So, because after you entered in this one, I tried entering in this.
Okay, let's
It didn't work. And so
okay, let's do this first. Open terminal here.
Yeah, so if you COD 0
It starts at 0. Always starts at 0.
And then 4, 5, 6, 7.
You guys want to
So
get
each one is
with
with
it's all included. Pizza, if you guys want pizza right now.
Okay.
Okay,
Because when you're dealing with binary, it always,
let's do.
when you're dealing with binary, you always start with 0. So that's how we got that. So she said go on to the next step. I'm gonna go.
Okay. Close window. Disassemble the main function, and we look for the stir copy, which is right here. So let's put a breakpoint. So then that way it just stops prior to getting copied over. Okay. So do you understand where the ESP is yet?
No.
Just by looking? Okay. So the ESP is always right here in this top corner.
Okay.
So right here. So this would be the address of ESP, and we can
Okay.
confirm that just by doing P ESP. Whoops, copy that instead. And as you can see, F040, and that's this address
Okay.
right here. So this is where your stack pointer is.
Mhm.
Now, every time a stack's created, stack pointer and the base pointer go to the same place,
Mhm.
and then it opens up like this. So and you can see 098. So it starts at 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is your base pointer. This is your stack pointer. So this is our stack right here.
Okay.
So what we'll do now, I'll take you right down to the bottom here. It says you suck, X is still. So what we'll do, take this one in. Oops. Okay, so let's display. Now let's do P and Z. Now here is our 05C. So come here to 05. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's our C over right here.
Mhm.
So this is what we're trying to overwrite here. So let's hit next instruction.
Is that a run a?
Yeah, that's what we put into
Okay.
the buffer. And as you can see now, Z is overwritten
Mhm.
right here. So we hit continue, and you have completed this challenge. Z is overwritten. All right,
Thank you very much.
no sweat. Okay, so where did we leave off? We found Z right here.
Yeah.
Okay, did you find out where it was?
Yeah. This was the one. Right?
That's the
So,
zero
yeah,
right there.
Yeah.
So now
And then
we,
you mentioned, yeah, this is the one, which is the base pointer. No,
the
sorry,
return address.
The return address. Yeah.
Yep, okay, so nothing's been copied there yet. So let's do, oops. Oh, I'm not used to your mouse. Here, you do that one. Just click the next instruction in.
Yeah, we'll go for it. Yeah.
Okay, and then if we just do, now you can see these 41s are copied in right here. See, this is our A's that just
okay.
got copied onto the buffer.
Oh,
And as you
okay.
can tell, we're going to need a lot more, right? So what we'll do, we'll just hit C here,
Mhm.
like so. And it says you suck, X is still 0.
Okay.
So let's copy that one.
Okay.
And let's put that run into, so now we're just putting 52 A's into the buffer.
Okay.
Oh, hold on one
Oh,
sec.
okay.
I got
It is the space. Yeah.
space there. So just, okay. So now just copy this one here. Okay, so there's our stack, and we're right at the stir copy before it copies in. So nothing's been copied there yet. So when we put in next instruction, just hit it. Here, I'll just do NI,
Okay.
and then display. You can see all our 41s are filling the buffer,
Yeah.
and we've overwritten the variable.
One. Okay.
So if we hit C, you have completed this challenge. Z is overwritten with 4141. So that's how you overwrite things on the stack.
Okay.
So what we'll get into next now is overwriting that return address with shellcode, and then we
Okay.
start totally hacking the system. All right. Okay, so that was a bit of fun. We'll jump right into our next class here. Okay, so now we're getting into the serious stuff, the buffer overflows. So anytime you've ever heard remote control execution or ran a script on a program from Exploit DB or somewhere like that, this is what they're talking about. Okay, so buffer overflow. Instead of overwriting a random variable on the stack like we just did, we're going to overwrite the return address. And where's the return address? Can anyone tell me?
Right to the base.
Right next to the base pointer. Always to the right of the base pointer is where it's at. Okay, so I am not an artist, so don't laugh at me too hard. But okay, so what you just learned is the top here, we see the ESP, we have our buffer that we filled out with A's, our base pointer, and our return address. So what we're going to do is we're going to put X90, which is NOPS, which tells the computer in assembly no operation. So basically when it gets to NOPS, it just keeps going until it gets a valid command, okay? So this is done basically, it's called a NOPS sled, and it provides a place for the instruction pointer to land on and then slide into our shellcode. So this is the vanilla buffer overflow. You will not get away with doing this nowadays, but this is part of the process of learning how to do it. And we'll get into bypassing that stuff soon. So the way it is, we set up our NOPS at the top of the stack. So instead of just putting in A's, we're going to put in NOPS. We're going to put shellcode right after that. and then we're going to fill up the rest of the buffer with just a couple A's. The return address, we're going to do a jump in assembly, which is going to jump back to here, come through the NOP sled, execute the shellcode, and take over the system. Okay, so that's the basic idea of a buffer, vanilla buffer overflow. So let's get into it. Okay. Okay, so the first thing we're going to do, we're going to make sure that ASLR is turned off. Let's open the terminal. And all you do for turning off your ASLR, everything's a file in Linux, a folder. So basically, you just echo 0. It's either 0, it's off, or 2, it's on. So we'll echo 0 into the file, and you can see cat right here that it's 0. So ASLR is turned off. That's our first step. Next, we compile our binary. I've already got mine compiled. So we'll jump into our GDB where we all live as exploit developers. And again, we disassemble the main function here. And thankfully, we have this thing called vulnerable function here. It looks like something we should check out as exploit developers. And here's our stir copy again. So we know that this is vulnerable to buffer overflow. So we'll just copy this and put a breakpoint at it so it stops just before it copies into our buffer. And what we'll do, we're going to skip over one part here because when you're doing exploit development, if you ever hear of MSF Venom and all the tools in Kali, you'll use MSF pattern create a small buffer that has repeated numbers and letters. You send that into the buffer, and then whatever overwrites to EIP basically tells you how big that buffer is. Okay, so we've already done that. And we come back that the buffer is 268 bytes. So what we'll do now, we'll send a skeleton in. And as you can see right here, we have 268 A's and then 4 B's. So the 4 B's will be the jump backwards into the NOPs. And this will make sense here in a sec. So let's examine 132 words from the ESP. Now, and I should point out too, a word in 32-bit is just 4 bytes, okay? So as you can see, nothing's been copied into the stack yet. So let's hit next instruction. Have a look again. And as you can see, here's all our A's copied in here. And overwriting the return address, we have B's, which is the 42 here. So now we have control of, this is a skeleton to basically show that, yeah, this works, it all lines up properly. And now we have control of the instruction pointer. So now what we have 268 bytes we need to break down. Our shellcode here is only 35 bytes because just a binsh shellcode for example here. If we're doing this in real life, you need about 300 bytes for a proper interpreter shell to get back from interpreter shell. You can get smaller ones, but it don't have the same functionality as the interpreter. So what we'll do, we're going to put 200 NOPs, our shell code, and then 8 A's, and then a jump that's going to jump back into the shell code. So let's continue on here. And as you can see, a segmentation fault. So if you were an exploit developer and you were doing this kind of work at home, you would just constantly barrage the program until you see that segmentation fault. Once you see that, you're like, oh, okay, I can exploit this. And then you start writing your exploits. So now I'm going to run it. And as you can see, we have 200 NOPs right here, which is X90. We have our shell code right here. And then we have 33 A's just as a buffer, because you can't have gaps in the space, right? And then we have these B's set up here that we'll find a jump address to jump back into our shell code with. So let's examine our stack. And nothing's been copied in. Let's hit next instruction and examine our stack again. And you can see these 9 zeros right here. These are all our NOPs, right down to here. Here's our shell code on the stack here. And now we had to fill it up. You can fill up this buffer with everything. Exploit developers always use A's, B's, and C's, though. So I filled the rest of the buffer up with A's right here. And then this right here is the return address that we have overwritten with our B's. Now I'm going to find a jump address. So I'll just open up my notepad. Now we need to jump backwards into those NOPs. So you'd never go with the top because things in binary exploitation shift a little bit. So if you go with right at the top, it might shift a bit and totally mess up your NOP sled. So what you want to do, you want to come down here to the center and pick one. So I like this one right here. Okay. And now everything's looking good for this vanilla buffer overflow. So we'll continue on and exit the program. It crashed again, so we know that it got to the return address and realized that, yeah, there was no proper instruction there, so it just crashed. So now what we need to do, we need to add that jump address. Now, what I'll do now is show you a slide. This is probably the hardest part. So the core concept of little endian means the least significant bit to little n is stored at the lowest memory address. So 0xb7dd3920 becomes 2039ddb7. So it's stored backwards into the stack. So this is probably the most complicated part of this. And I'll show you a fun way to do it with Python where you don't have to do any of this stuff. But this is the core concept of when you look in memory, if you had to store it just B7DD3920, you would look at it in assembly and it would be stored backwards. Okay, so just a little something to keep in mind here. And let's see if I mess it up or not. So we already copied our address down from the jump earlier. So right here, one, two, three, four. X90. EE. FF and BF. So let's put that into the program here. Let's examine our stack again. And nothing's been copied in. Let's hit next instruction and examine the stack again. And as you can see, here's all our NOPs here. And this is a good time to make sure that your address is perfect. There's our shell code starting here. Here's our 30 A's right here. And right here on top of the return address, let's double check and confirm. And as you can see, I didn't fuck it up. So BFFEE90, we're good. So everything's good and copacetic. So if I hit continue now, you can see user bin bash, we now have control of this server. So if this was on a server somewhere, we have a full interpreter shell and we own it, okay? So we'll break into our groups again, and I'll walk you through all this, and we'll do our first vanilla buffer overflow, hopefully. All right. If you want to jump up on mine. Okay, just have to start at this one right here. Just that one right there.
This one?
Yeah. Actually, here, let me set you up proper. Here we go.
Leigh,
Yeah.
before you go any further, I just want to tell you there's somebody on stream that just said awesome live stream. So I'm assuming that somebody really likes what you're teaching right now.
Good, good. Okay, so now we got to compile it. We got to. Oh, you're already ahead.
No.
Oh, this is the old one.
Yeah, it's the
Okay,
old one,
so this one is exploit 1. That one right here, exploit 1 class.
Oh my. Okay. Yeah.
Yeah, that's fine.
I usually don't.
Yeah, so just get your screen set up and get it compiled. Terminal right here in the corner, that one, or down, right there. Here we go. Okay, so now you're going to disassemble the vulnerable function, which is this function here. So just copy that right there. There you go.
And so it's not this here.
No, just the name of the function. Okay, so now we're going to look for the stir copy, which is right here, and B star, and take this address right here and set a breakpoint. So we'll do B star and then copy this address right here. Perfect. Okay, so the breakpoint set. So let me just, so now this is where we would fuzz, but we're not going to get into it because it means another class. So basically we came back and found out that the, oops. Okay, so now examine it and then hit next instruction and then examine it again, and you should see the A's go into the stack. How we doing, guys?
So like, yeah, we just set it up. So like, we're gonna open the new terminal for this one, right?
Yep, in
Yeah,
your binary,
in
and grab this one. So that's compiled, perfect.
Okay.
Now open up the GDB. Perfect. So now we're going to disassemble the main function.
So GDB is a tool.
Yeah.
The binary exploitation tool, yeah.
Yeah.
Oh, got some messed up
Yeah.
stuff there. Okay, and you see vulnerable function. So let's just say disassemble the vulnerable function. Nope, just click this one right here.
Oh.
This. Perfect.
And then it shows.
Now you're looking for your stir copy, and you got to set a
Stir
B
copy, yeah.
star at that address right there.
Where do we find ESP.
Oh, hold on now. Okay, so
Okay.
here's your stack. And as you can see, nothing's copied into your stack yet. So
Okay.
hit next instruction. And I just use up arrow like that. And as you can see, here's your,
Okay.
it's copied in.
Yeah.
The return address has the 42s on it, and these are your 258 A's.
Okay.
So now you know the instruction pointer you have written in your 42s. This is where you're going to put your jump. Your jump's going to jump back up here to the top into the knobs and hit the shellcode and take the computer over.
Okay.
So what we'll do now is if we just come down to this right here. So 268 bytes is our total shellcode. We have 200 knobs, 35 for our shellcode here, 8 A's to cover up to the 42s. And then the 42s is where the jump's going to go. Okay, so let's grab this one here. Okay, so now this is our skeleton. Here's our shellcode. We have 200 knobs, our shellcode, 33 A's just to fill out the gap between the shellcode and the jump. So I'll get you to examine the stack, hit next instruction, and examine it again and see where it all lines up, and then we'll go from there.
I think the thing is, you might want to recopy that with no extra spaces.
Yeah, this one.
There, that should be good.
Okay.
See. Scroll down a little bit.
I am trying to scroll down, but I don't see here anything with this color.
Here, just let me see.
Okay.
It already went to the next prompt. I don't know. We don't know how that got in there.
Okay, so
So we're
what we'll
hoping
do,
we're hoping that doesn't actually quit it, because sometimes it
do
just
that. Terminal.
I just start over.
This will only take a sec.
Because it's already compiled, right? So, okay, so getting that one.
Disassemble the main function. Disassemble the vulnerable function. And now breakpoint at stir copy.
Yeah.
It's hard to see in this font.
Yeah, I didn't choose that font. Okay, I'll be honest.
He was trying to change the color, too.
I'm trying to change it, but I didn't choose that font.
Here's the breakpoint set.
Try to change it, but no, yeah.
No, okay.
Yeah.
So this is where you would fuzz it. We're skipping that for this class because
Okay.
we didn't really have time. This is usually like a 2-3 day course we do.
Fuzzy
So
thing,
now-
by the way.
Yeah. So now we just put in 268 A's, that's the size of our buffer, and then we overwrite our return address with these B's. So what's going to happen, we're going to put the return address is going to be where the jump backwards goes, jumps back into NOPS, and then hits shellcode and takes over. So actually, I'll let you do that. Copy that one, have a look at your stack, hit next instruction, have a look at your stack again, and see where everything lines up. How we doing, guys?
So we're trying to figure out which one is the jump
Okay.
address.
So
it must be the-
what you got to do, you got to come up here to these knobs up
Mhm.
here and find something in the middle. You never go for the top here because in binary, things can move like 10 bytes
Mhm.
and it'll fail. So this one right here is good. So I would copy that one.
So any of these basically?
If you took any of these in the middle
Mhm.
into these knobs, it'll work.
Okay.
So then I just open my mouse pad,
And you paste it. Okay.
just paste it in here just so we remember.
Just a reference.
Okay. What happened?
And then it's in reverse.
So what's going to happen? Here's our 42s. This is
Yeah.
where that jump address
Yeah.
needs to go. And then it'll jump up
So
here.
it goes before there or it gets overwritten?
we're going to overwrite that jump address onto the return address. Okay. So what we'll hit continue here. And continue. Okay, we got a segmentation fault. That's always really good. Okay. Okay, so now here's where we have to put that jump.
Okay.
So like this. Now
It was this.
was this? Oh, it was too. Okay, so this is Little Indian convention. So we start off with the first two, and it goes like 9-0. So we keep them in blocks of 2. So
9-0.
the first one, just here, I'll let you do it so you remember it. So 9-0. Oh, X. Keep the X. Keep the X. Yep.
9-0.
Okay.
And then BF.
BF. After the X, though.
After the X.
There you go. Perfect. Perfect. Okay, let's run that. Let's examine that. Nothing's copied in yet. So hit next instruction. Examine it again. So here's our NOPs. Here's our shell code.
And this is what we just
Here's our 4 ones. So now is a good time. You can have a look and see BF, FFEE 90. You overwritten it perfect. Okay, so now the program's going to crash. It's going to hit this address, jump back up to here, go through these NOPs, execute the shell code, take over the system. So just hit C. And boom, you just took over to the server. Wow. You own it. That's your bitch. Easy as that.
Cool. We got a question here from from YouTube.
For the webs?
Yeah. So there's a question here that says, does it require C language? Like, do you need to know C language to be able to actually perform this?
Not at the basic level, but you need C and assembly to really get the most out of this.
Sounds good. And then the other thing that came up is that you look like a very intelligent woman. So
looks can be deceiving. Okay, so what we'll get into now is, so we figured out that it was 268 bytes to our return address. So we're going to fill 200 NOPs. We're going to put our shell code right after that. And then between the shell code and the return address, we have to fill it out with something. So we'll fill it out with A's, 33 A's. And then we're going to put the jump to the top of the shell. Okay, so what that looks like is this one right here.
So the code which we ran, so it ran well, but we didn't meet that, the cracking that one?
No, this one, we don't have the jump address put back in yet. Okay. So where these B's are is going to overwrite the return address. We're going to put a jump back to the top of the NOPs.
Okay.
It'll go down through the NOPs, execute the shell code. Okay, so just watch. It'll become clear. It'll clear as mud. Just give it a sec. Okay, why is it that? Oh, there we go. Okay. So now let's examine the stack here. And as you can see, nothing's copied in yet. Now it'll become more clear. So as you can see, here's the NOPs. Yeah. So these just tell the computer no operation, move on to the next code. Okay. Once we hit here, this is our stored shell code. This takes over the computer. And then we had to fill the buffer with 41s right up to here. And here's our stack or our return address. This is where we're going to put a jump. So right now we got to look for a jump. So this address right here.
So you're just choosing a random address?
It has, what I always recommend is never go with the top address, because things in binary will shift 10, 20 bytes sometimes. And if you go with the top one, it probably won't work. So you want something in the middle. Any of these in the middle will work. So We'll copy that address. Do you have a mouse pad on this or a text editor? Actually, I can just open another terminal.
You just followed your instructions. So if the instruction said that text editor, then it would be
Okay, so we'll just PUD. Okay, so that's the address we're going to PUD onto this jump. So now this is the hardest part. We have to do the little Linnean stuff. So just hit C here. And the program's crashed. That's always a good sign when you're doing exploit development. Okay, so here's the jump address right here. So now 1, 2, 3, 4. So now what we do is we take this, we put 40. 40. Where's the terminal? F0.
okay. So like you're reversing. Okay, got it. Okay, F0.
F0. Let's have a look. I wish I had a better memory. FFBF.
Yeah.
Okay. So now we come over here. We do FF
and BF.
and BF. Perfect. Okay. So now just examine your stack. So you're examining 136 words from the ESP. No, nothing's copied in yet. So let's do next instruction. Let's have another look. So here's our NOPs. Our NOPs are all right here. Here's the start of our shell code. Here's our filler that comes down. And here's the overwritten address right here. And we can just double check to make sure it's right. BF, FF, BF, FF, F0404. So let's double check.
Yeah, that's
Perfect. And it's perfect. So let's hit continue. And there we go. You own the computer. The computer is pwned. So that's how you take over a server with remote code execution. So anytime you hear like there's a remote code execution out, that's exactly what's happening. Okay, now this is the vanilla version that would have worked up till 2004. I'll show you the next steps now. Okay, so we just owned our first server. What we're going to move on to next, just let me exit out of everything here. Okay, so
we have another question
Oh,
from the audience
okay.
On YouTube. So the question is there a roadmap for learning this, like that you may have or you know online that you could potentially find?
The reason I put, this is usually a 3-day course, and the reason I put it together is exploit development is always looked at as some like weird thing off in the distance that only gods do. It's not. It's really quite simple. If you go to my YouTube, if you check out my YouTube, I have lessons from the very beginning up to more advanced stuff, and that'd be a great place to start.
If you want to share it with me, I can probably put it on in the chat for them to be able to check it out.
Yeah.
When you have a chart.
Just actually, could you Google Leigh Trinity?
Yeah, and put it in the chat.
Yeah.
Okay.
Okay, so let's get okay. So what we learned, we all learned where the EBP is, the base pointer. We learned where the stack pointer was. We learned the return address is always next to the EBP. We also learned that counting starts at 0 in binary and not 1. And we learned how things are stored on the buffer. And you did your first buffer overflow. Next, we're going to move into data execution prevention. So of course, people start putting shell code onto the stack. Computer companies had to come up with a way to get rid of that. So they developed data execution prevention. So data execution prevention, it was introduced in Windows XP in 2003 to prevent what we just did, okay? So now we cannot execute shellcode on the stack. We can't put a shellcode on and execute it because of this prevention. So of course, already, this came out in 2003. A method to bypass this was actually developed back in 1997. So as you can see, the attackers are ahead always. And it's called the return to libc method. So what we're going to do now is use the computer's own code to make shellcode and take over the system. So let me get set up here. Okay, so this is the depth bypass right here. So as you can see, here on the top is the way the buffer is normally laid out. We have the EBP and the buffer, the return address, and then after we return address, we have argument 1 and argument 2. Argument 1 is basically the name of the program, and argument 2 is its vectors that we won't really get into. Just know that the next two after return address are argument 1 and argument 2. So what we're going to do, we're going to fill the buffer with A's again. Over to return address, we're going to grab the code, return-oriented programming code for system, which is built into the computer itself. We're going to use the own computer's code against itself. We'll put an exit function next to it, and then our favorite binsh, which spawns a shell. So now that we can't put that shell code there, we'll use the computer's own code against it and cause a shell that way. And it'll become more clear once we get into it here. Let me just open up our dep. Okay, so just let me open up my terminal. Okay, open up our GDB. And you can do something called checksec here, I'll show you. And in Linux, dep is called NX. So you can see NX here is enabled. So now if we were to try to do what we just did, it wouldn't work because it would detect an executable shellcode on the stack and it wouldn't do it. So this is when computer companies came out to stop people from doing it. So let's disassemble our main function again. And disassemble our vulnerable function. And let's look for our stir copy. There's our stir copy. So I'll set a breakpoint there. And now I'm just going to put in an input of 40 A's into the program. So I examine 80 words of hex from the stack pointer. Nothing's copied in yet. So let's print the EBP. 058. So that's down right here. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So here's our base pointer. Can anyone tell me where the stack pointer is? It's always in the top left-hand corner right here. Okay, so there's our stack pointer right here. So we got our base pointer, our stack pointer, and here's our stack right here. So let's hit next instruction and have a look at our stack again. And as you can see, our A's are copied in here. So that's definitely not going to reach. So continue on here. So let me undo my mess here.
The stack pointer is the first at the beginning of the stack and then base pointer is where you set your break?
Yep, your stack pointer is always right up here in the top corner, the first address. So what happens when a stack is formed? The stack pointer gets put onto the stack, the base pointer gets put to the exact same spot, and then it subtracts the base pointer from the stack pointer. That's how a stack is framed. Okay, so we're going to put in 280 A's this time and see if we can fill up our stack this way. Okay, so nothing's copied in yet, so it hits next instruction. Now let's find where our base pointer is. It's at EF68, so you look for EF60, 0, 1, 2, 3, 4, 5, 6, 7, 8. So right there. So I need to take off 12. This right here is the base pointer right here, and this is our return address here. This is argument 1, and this is argument 2. So always to the right of your return address is argument 1 and argument 2. And these are what we're going to overwrite. The return address we're going to overwrite with the address of system. The next, we're going to provide an exit function, and then we're going to put binsh onto our argument 2. So now we know the size of our buffer. We can continue on, and as you can see, a sigsev. So basically what happened was the computer read the return address and seen a bunch of A's and went and died. So what we'll do now, we know 268 A's should fill it up. So let's examine our stack again. Next instruction, examine our stack. And as you can see, we're filled up pretty good there. So here's our base pointer. So here's our return address. Here's argument 1. Here's argument 2. So this is what we're going to overwrite now. So next, we'll send in a skeleton script. And this is the same thing we did before, only this skeleton script, we're going to use B's for our system, C for the exit, and D's for our binsh. And let's open up our stack and have a look. Okay, so now we have all these A's filling up our stack. Our return address is overwritten with 4 2s. This is where we're going to put our system. Our 4 3s is overwritten. This is where we're going to put our exit. And this is where we're going to put our binsh. So now it's a little different in other programs finding these, but what we'll do, we just hit P system. And we'll open up a mouse pad here. And we'll copy system. So this is what we're going to place on our return address. Next, we provide an exit for the function. So we need to look inside the computer's code and find the exit function in Linux. And here's the address for that. Perfect. And now we need to find the address of binsh within this computer. And it's right here. Okay, so we have those. Let's continue on. And we will quit out of this. Now, basically, whoops. What I'm doing now is I'm going to take this input and put it into a binary, a payload binary. And that's done there. And next, we're going to run the program with it as an argument. So let's disassemble the main function again. Disassemble the vulnerable function. Find our stir copy, and we'll set our breakpoint again. Let's run the program. Examine our stack again. Nothing's on it. So let's hit next instruction and have another look. And as you can see, our A's are all filled up. Our return address is overwritten with system. So B7DD3920. Everything went well. Everything's copacetic. Our argument 1 is overwritten with exit, B7DC2D60. That's perfect. And next, B7F3CFAA. So everything is good. We should get a shell. So now we just bypass data execution prevention. Computer companies stopped us from doing it that way, but hackers already had it figured out in 1997 that we can do return-oriented programming and take over this computer that way. So what did we learn? Let me just haul up my slides here. So the big takeaway, basic return-oriented programming. We can't execute shells, so we took pieces of the computer's code and made our own shell. And of course, little Indian format is still a pain in the butt, so you got a little experience doing that. So we'll break into our groups again, and we'll go through this one. Here we go. So now we'll try that on our own. Thanks for coming out.
Yeah. So I did the initial things. So like I even set the breakpoint.
Okay, perfect.
And, yeah, and now
Awesome.
like this is the one which I should be running. Okay.
Awesome. You're pro already.
Oh, thank you. See, like, I do have a good.
You had a good partners
teacher.
too?
Oh no, the teacher was amazing. So that's what I would say. Like so.
Great job. Okay.
So if I see this one and
We'll examine our stack. Yep.
So what I've understood is that like we run this code just to test it, and given this info, we try to change the code, and then we improve the code. Is that what we're trying
Exactly.
to do?
Exactly. Yep.
Okay. So here we check it, and we don't really find anything, and that's why we kind of investigate, or at least to get the layout. And
Exactly.
Then
This, or is it this?
Okay, just give me 1 sec. Okay, help me make it out, guys.
Is it this one or this?
That's the one. This one right here
This
on
one
this side.
here.
Yep, perfect. Good job.
Yes, yeah. Is there a space here?
Yes.
so here, yeah, this is the one that we ran. So like now we're gonna check it. Check the.
I just hit this one here, actually, just the next instruction. Now, what I do is just, we already examine our stack. You want to keep looking at your stack, so just hit up. And now we can see our A's are copied in, right? So let's grab the EBP, find out where our EBP is.
No. I just finished.
It's 098. That's what it says.
Yep. So let's find that on the side here.
098. Okay, so it's gonna be here. Okay. 0. I see 090. Yeah, yeah. This is the one.
090, that's
Yeah,
one. So
yeah.
0, 1, 2, 3, 4, 5, 6, 7, 8. So that's it right there.
Yeah.
So there's your stack pointer, there's your base pointer, and this is the area we got to fill up. So as you can see, we need a lot more A's. So
Okay.
we'll just hit continue here. And let's grab this one and do the same thing.
So the EVP is this first one, right?
ESP. ESP is here, and then we just hit grab EBP.
Okay.
So that's 058. So 5, 0, 1, 2, 3, 4, 5, 6, 7, 8. So there's your base pointer there. There's your return address. There's argument 1. There's argument 2.
Okay.
So what I would do now, just hit C there. And then come down and grab this one here. So now we're going to put 280 A's onto the stack. So basically put it in, do the examine. There we go. And you can see nothing's in there. Just hit next instruction. Examine again. Perfect. Pro already. Okay. So now just hit find out where your EBP is. So F68. So we can see F60 here. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So you've already overwritten it here. So just hit C.
Sorry, how did you know?
Okay, so EF68, right? So we
Okay,
come
so
over
you
here, we
come to
see EF60.
Okay.
So 0, 1, 2, 3, 4, 5, 6, 7, 8. That's your base pointer.
Okay.
That's your return address. That's your argument 1. That's your argument 2. So just hit C and then go down to the next input. That one right there. And do the same sort of examine.
Okay.
I'll be right back. Okay, so where are we?
So yeah, so here I did run this one, and then we are looking into the pointers.
Okay.
So like previously, our means like our base pointer was 0908. That's what I tried it, but it is still yeah. I believe like this is the thing that I'm changing. Yeah.
The 19-year-old is on one and then the other ones at 10 and 13, they're still not interested either. So
I don't know how to
Yeah.
change it on that.
Yeah.
Okay, so to print EBP, it's at
it is 0908, or did it change? I can.
EF8. So let's tell you what we'll do. Oops. Okay, so what we're going to do, where that's hard to see, we'll move on to this part here. Okay, so now let's do.
So we went here because we tried this one and then it still didn't fulfill our purpose. So that's why we
move on
improved
to the
code.
next one.
Okay.
Yeah, and that's what a lot of exploit development is
Okay.
do this, didn't work, do this, didn't
Okay.
work, do this,
Okay.
didn't work. Okay, so let's just hit next instruction here and have another look. And as you can see,
Oh yeah.
all
so
our
this
A's are
is-
filled out to here.
Yeah.
Our return address is overwritten with the 42s. This is where we're going to put system.
Okay.
43s is overwritten with exit because it needs a place to exit, the function does.
Okay.
And then our 4s is where the bin sh was just shell. It goes, okay? So what we need to do now is hit print system. Do you have any kind of text editor on this? Tell you what, we'll just do this. Here we go. We'll just put it in here for now. Okay. So now you come over here. We do P system. So now we need to find that system that overwrites the return address. So copy those down. Do the same for exit and binsh and copy those down into that open file I just had open. And then we'll go from there.
Is it okay if I use this?
Yeah, that's perfect. Perfect.
So we're copying this, this, and this, correct?
Perfect. Awesome job.
So this is the system. And this is the bin slash.
Perfect.
Okay.
So you can continue on and exit the program out. Yep. Perfect. So now let's go down to this one right here. I already have the addresses put in there. What we need to do, we need to open a new terminal. And this is just putting that into a binary file for the exploit. So you can start running the...
Back on the original.
We can kill this one, actually.
Okay.
Okay, so this is the last few before you take over the system. So let's start with that one right there.
Okay.
So we're running the p exit right now, right?
Okay.
Yeah.
Yep.
Okay. And we copy this one. Yeah. And then we find the find bin.
And it's right there in green.
C is the continue, right?
Continue on. Yep. Just to exit the program. All right. So let's have a look at the file here. These should be the same, I think. So I already had these put in.
Okay.
So as you can see, we have 268 A's.
Oh.
Then we have our system,
It is in the reverse format, right?
reverse format, a little
Okay.
Indian format. So we can copy this one now. Now what we need to do, just exit out of GDB. Because what happens, we're going to put this into a binary file, which is a little... Normally, like I said, normally I have a couple days to play with people. So, but... okay. So now that's catted into a binary. So now just run through these and we'll own the system. Okay. So we got to disassemble the main function again. Okay, so disassemble. Oh, that didn't work. Now, let me just try something here. Close window. Here it is. The terminal here. Here we go. Okay.
don't think it's right?
Because this is shell not.
Shall not found, and do a try and work a number. Oh, it says, okay.
Just give me 1 sec, guys. I'll be right there. Okay, so payload.bin is made.
There you go. So you have your shell. Just you have your shell.
Did you guys take it over by yourself?
Who am I? Who am I? No, who am I? Like, so see, you got a shell.
It says the file command
You
is
know what
not
would be the
there.
next step for this?
Don't know what's
Would be
happening
to
there.
Find out how to allocate your shell and then keep consistency, right? So go take a look at the Python script. Oh, maybe that's not. Should I tell you? I guess I could tell you. Okay, give me a second. It's Python 3-C. Yeah, Python 3 space -C space single quote. Yeah. TTY.
I don't know why this isn't working on your.
Oh, shit, I forgot. Give me a second. I'll go find it again.
Did we have to disable something in that first, like in the check? Did we have to do anything? Check sec.
I'm trying to remember by heart. I just forgot.
That's done.
Okay, so it's after the single quote, it's import space TTY.
Okay, the binary file's made.
TTY
Running with arguments.
SPAM, sorry, SPAWM. It's bracket, double quote, / no, I'm sorry, it's a double quote. Apologize, it's the bracket. Then double quote. /
Program is not running.
/ dash. Double quote again. Close the bracket, and then single quote.
I have no idea why yours isn't working.
There we go. So you just elevated your shell now, right? You can see a little bit different, so you have a bash. So that's how you can start with. So right now, you did the SH. Another thing that could have been done, let's say you are there. Another thing that could have been done is to get yourself a remote shell now. Okay? So you exploit that thing, you could get yourself a different shell.
Yours is called Deb?
If you think about it, how could you transfer files?
I have no idea why yours isn't working. Oh, file name too long. I ran into this before. Oh, I see. I think maybe. Hold on.
Let's say I'm Callie, right? I have Callie, I just exploit this, and then I see that that's working. How can I get files onto that shell now, or onto that computer over there? Sending them out. So that's good. I mean, like, that's fine. So, but that's the goal of it, is to understand the whole thing of how to be able to navigate or get around. So NetCap, you know.
No, it's coming out with file name too long on yours. I don't know why. I really don't know.
Where did you see that the file name is long? I could.
File name too
This
long
one, okay.
right here,
Okay. Mhm.
which is very strange. Let me just double check my command for a sec.
You can see the NC
Let
right
me
there.
seal this for a sec. Actually, I can't. Okay. I think I see the problem. I think there was a bit of a typo.
Control that binary and then basically send from your computer to that computer. Right? and then you could execute it. So if you need to do an exploit to be able to, because let's say you're
I
not.
think that might have been the problem.
That would be one thing. So do what do we do? Enumeration step could be uname space -a, right? Could be one of those things. So if you're trying to understand.
There we go. Okay. It was one little quote wasn't in the right place. Sorry about that, guys. So we just disassemble the main function. Edit, undo. Disassemble a vulnerable function. Okay, or stir, put a breakpoint at stir copy.
Okay.
That's not found. What was the other binary?
Yeah, the different one is at set.
Okay, let's hit run.
I can recall access. I think there's a bit more.
Okay, so let's examine the stack.
So you see here, this mention. So you could try to find out if there's anything. You could do ifconfig as well, right?
RMRF.
You know, do RMRF.
Not on my computer. Yes, yes.
So here we look into.
And nothing's in there yet, so let's hit next instruction.
There is one more for
And have a look at the stack again. We'll just hit up. Okay, so everything's copied in, and we can see we can check these right now and make sure these are all copacetic with what we had. So just hit, I think it's this file here you have open. So B7DD4920, B7DD320, we're good. Let me check this one.
2936. That is like 396, 3D60, and this is 2D60, and
Yep.
this is 3DFAA. This is 3CFAA.
I think if we hit C, we get shell.
Okay, let's see. Yeah.
Boom, took it over. It is now yours. Easy as that. So now you just bypass data execution prevention. And now we're going to get into the last lesson of the night, which is bypassing data execution prevention. And now they came out with ASLR because people start doing this, then they came out with ASLR. So we'll bypass ASLR next. Yeah, I have a YouTube where I have all the lessons laid out as well. And then I have a GitHub with all the commands and everything on it as well. Yep, I can give that to you after class.
Right? So now you may have a front-facing network, and then now you have another network from the inside that you may have to be able to navigate to.
Great job, guys. Okay, our last lesson of the night, guys. Let's mess it up. Okay.
Sorry, I took over a little bit.
It's all good. Nothing's broke on my computer. Everything's great. It's only a virtual machine anyway. I break those all the time.
US, but I'll plead the fifth.
Okay. So let me just get organized here for a sec, guys. Okay, the last lesson of the night. So address space layout randomization. It was first released on Linux as a PAX update in 2001, but we never really seen widespread, and it didn't hit Windows until 2007. So ASLR randomly rearranges the address space of key areas like the stack. So now you know how we just went in and grabbed P system, P exit, and those were all in one spot, right? Now every time that program loads again, it loads it in a different space. So now as the attacker, we can't go in and just grab it and put it into the next run because it'll be at a totally different address space. So that's what they came out with to prevent what we were just doing with data execution prevention. However, 32 systems can be brute force due to low entropy. So if we put it in a while true loop, we can go through all the possible addresses. I think it's 156 addresses is the max we would have to go through. And it's kind of fun to run it. Sometimes it runs like 2 minutes and you're like, did I mess it up? Like, why isn't this working? Sometimes it'll hit the address right away. So what we'll do is we'll set up a while true loop. We'll run through every possible address. And it's such low entropy that we can actually do that, okay? So let me just get set up here. Let's open our terminal. And if you want to open it up, guys, is ASLR class is the name of the... So the first thing we have to do is switch to our root. And now we have to turn ASLR back on. So we echo 2 into the... Oops, sorry, guys. Okay, now I have my root. So now I'm going to echo 2 into that folder. And now if I cat that folder, it should be 2 inside. There we go. Okay, so I'll change back to my user. Now, what I'm going to do, I'm just going to load up ping address here. And as you can see, the past 2 times I've loaded this, they're at different addresses. So this is what it came out with, so attackers couldn't just guess or couldn't go in and pick system and exit like we just did. So now every time this program's loaded, it's going to be loaded at a different address. But if you notice at the very beginning here, both of these start with 0xb7e. So the end of the address is actually changing, which is really low entropy, which allows us to take over. So I already have mine compiled. So let's open up our PETA here. And we have to set disable randomization to off. So again, we're going to disassemble our main function. And again, we're thankful that it says vulnerable function. And we'll set a breakpoint at our stir copy. And I'm going to put a Python input of 20 A's into it. So let's examine our stack. So here's our stack. Let's hit next instruction and have a look at the stack again. And we can see our A's there. Let's find our base pointer. So 2F8. So let's find 2F. Here's 2F0. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So here's our stack pointer. And here's our return address. Here's argument 1. And here's argument 2. Perfect. We know where everything is. Okay, so now I know to overwrite it. I need 20 A's. And then we'll put our skeleton in. This is the exact same way. So we're going to bypass dep and ASLR at the same time now. So we definitely need our system. We need our exit. We need our binsh still. But what we're going to do, we're going to put it in a while true loop and just brute force it. So let's have a look. Nothing's on the stack. Let's have a look at the stack again. Okay, so there's our 4 1s. Our return address has the 4 2s. Argument 1 has the 4 3s, which will be where we put our exit. And the 4s here is where we're going to put our binsh. So again, we need to find system. So let's copy these down. and exit again. Here's our exit. And binsh. Oops. Okay, we have our 3 addresses to, whoops. We have our 3 addresses to bypass dep. So this is called return-oriented programming, and it's a lot of fun. If you ever really want to get into it, there's a place called ROP Emporium, and it teaches you all the basics of return-oriented programming. And it's basically taking little snippets of code from inside the target computer and using it against the target computer. It's a lot of fun. So what I'm going to show you now is, this is more realistic. What you're going to be doing if you were getting into exploit development is using Python to send your scripts to the server, right? So you set up a connection, but you basically lay things out the same way and just send it in. So as you can see right here, within Python, we have this beautiful thing called struct and pack. And what that does, it takes the straight address that you find, and it puts it into little Indian for you. So you never ever have to go and take it and put it into backwards. You put it in here, you use struct, and it does all the work for you. So no fat fingers are going to mess it up. So what we'll do now, we'll use this script. You should have aslr.py downloaded. We'll use that script. We'll put in our system, our exit, and our binsh with our 20 A's at the beginning. And then what we'll do, we will run the program in Python, and it outputs it to a text document for us. So what we're going to do now, this is fun. What we're going to do now is we are going to brute force the ASLR. We're going to bypass the dep and take over the system. So as you can see, I have a little while true do, run the program, and use ASLR as a argument, or the cat ASLR.text as an argument. And as you can see, it's going through every single possible iteration of system. It's not finding it, it's not finding it, as you can see. So low entropy. So segmentation fault, it's boom. We have system shell. So now we just bypassed data execution prevention, ASLR at the same time. So that's our last class for this afternoon. Let's, what I'll do, let me just haul up. Okay, so what we learned simple Python scripting. We learned that we can use struct instead of using the fat fingers trying to put it in. We can use struct.pack to make it little Indian. And we learned that 32-bit systems, which you will find in any IoT device out there today, has very low entropy, and we can bypass every security mechanism on it. So we'll break into our groups, the last one for tonight, and let's bypass all security features. And that'll be a nice place to finish off the night with.
All right, we got a question from the audience on YouTube.
Sure.
And earlier was about C. Now it's does understanding assembly language required?
Crucial.
Crucial. That's
Crucial.
the answer.
Yes. And I plan on putting together a 32-bit assembly course sometime this year when I find some time.
Only for Intel?
Intel or ANTC syntax as well. Is just a little flavor. It's like real French and Quebec French.
She is a truly remarkable woman.
Oh,
You got a fan right now.
thank you. Okay, so let's break into our groups. We'll finish off the night strong.
You need anything, water bottle or something like that?
No, I'm good. I'm good. Give you one of these too. That's my website, exploits.ca.
Thank you.
One of these too.
I'm with him. So.
I'll give you one of my stickers as well.
Awesome.
You want one of these?
Yeah, thank you.
So for those that are not here, this is basically the sticker that you're missing out on. I don't know if we see it well enough on the screen, but
So ASLR is already turned on
Okay.
this system. So we can go down to
And
this one.
I'm already enrolling everything.
Yep. So we can go to
This one.
that one right there. Awesome.
Okay.
So set disable randomization off. Then it's right into disassemble the main, vulnerable function, and the stir copy again. Okay. So as you can see, let's hit that again. Whoops. Yeah, just you can see these addresses. Now, every time it loads ping, it's loading it at a different address. But if you notice, the 0xB7 is the same. So it's only these here, and it's low entropy. There's only so many possibilities that this address is going to be at. So now as attackers, we're going to go in and we're going to brute force until we find the right one. This is what they tried to do to stop us, but we were ahead of them. Okay, so let's there you go, you got it.
And this one, it says that no debugging symbol found in ASLR. That's fine.
Yeah, that's fine. Perfect. So again, we're going to disassemble, set up your stir copy again.
So where?
Okay, so
The-
EB8, so EB0,
Yeah.
0, 1, 2, 3, 4, 5, 6, 7,
it's
8.
B, okay.
Yeah.
It's-
Sometimes you
it's
look down,
saying, so I'm
uh-huh.
like, okay.
Perfectly normal.
Mhm.
You guys are getting the hang of this quick. I like it. Okay,
So then we don't actually have to copy this down because your thing
it's
already has
already
it, right?
absolutely done. Yeah.
Okay.
So just open up aslr.py. And you can see this is a cool thing about struct. Use struct from Python. You can just write them in normal with pack, and it does it for you.
Okay. And so we can confirm looking at the terminal that they're the same.
Perfect.
Yeah. Okay. And then when it says add gadgets, it's adding these, right?
These right here. Yep.
Okay.
Yep.
And so we then add in Python to the
Okay. Oh, sorry. You got to have this one. It's not clear in my notes, actually.
Oh.
Let's try that one again.
Yeah.
Okay. Okay, I'm back.
So here I ran till then. So here, as these are all zero, so like that's the base pointer. Is that how you figure it out?
That's the base pointer. Yep.
Okay. So, but in the other ones, we had some other numbers, right? So like we were counting it. So like, how does it? I mean, how does it vary here? I have very limited.
It varies constant
knowledge, yeah.
every time it changes.
Oh,
Mhm.
okay.
It's just there's nothing stored at the base pointer, so it usually comes across as 0, right? So what we'll do, let's skip right to this one here. So segmentation fault, when you're doing exploit development, usually you're fuzzing the program. So you just send a bunch of garble at it and oh God, no thanks.
Well, I thought that you were really doing that. But, you know,
I'm-
sending it, I was like, oh,
Oh,
wow, that's
God.
like-
Okay, just copy that one.
Yeah. I really-
Yeah, I'm really that good.
I thought that was a form.
That's a pro. No, I was being a pro. I was being a pro. Okay. Okay, let's go back to the top for a sec. Exit out of this one. Okay, just let me have this for a sec.
So you can practice again. Yeah, practice to like you see this. What do you do? What's your next step again?
Okay, so let's get to the point where we're
Well, as much as possible, you're always trying to look.
oh,
to
why
elevate
is
your
yours
shell.
acting
So
weird?
this is basically one, and when I'm saying elevating is like stabilizing.
Okay.
Because if you try to do certain commands, eventually it might just crash, and then you're gonna have to redo again before, right?
Okay, so
So
let's
always
go over
trying to
here.
get to,
ASLR.py.
make sure the browser is stable as possible. So first one you can start with is if you know the Python is there, you do which Python 3, right? Try and figure it out.
So
which one is there. And then
here's
if it's not even,
this
you try as much as
is nice because you can just put the addresses in with this, so you don't have to put in 60 like that, right? Just use struct dot. So now what we'll do,
Right, no, it doesn't beat your root like you do anything right
I don't know why it's doing that.
now.
Oh, stop drawing.
Yeah,
There we go.
I don't think you are root at all. Like you have nothing, well, maybe you can do sudo su, sorry. It could potentially work, but you need your password, right? So you're not gonna be able to do that. So one of those things that you would do.
Okay, so now we should have a text file, ASLR.text. Okay, so now we have all those gadgets in there. So now just run that program in a while true loop. So now we're just going to brute force it. You got it already. See how quickly yours happened? So it's random, right? So like sometimes it can be going for like 2 minutes, sometimes like the first one, boom, and we got it. So now you have shell. So like is, who am I? VK. So this is yours. You just bypassed every bit of security features that Windows shows up with.
So, but this is. So it went VK into which one? Sorry, like, you know,
So like if this was a server,
Yeah.
I own the server now. It's not just a program. I own that full server. It's mine.
Oh, okay.
So this is the joy of exploit development. I took over a Chinese company 3 days ago through their database, took everything, absolutely everything. So I would sick in bed, like lit around, like dying, and I'd wake up and I'd do some search and go to sleep again. And so that's it. So that's bypassing data execution prevention, ASLR. So that's the security features that are out there and how we get around it.
What does it represent? Technically speaking, if it's not well done.
All the directions.
Do you see something in there? It could basically lead you to understand what command to be used to be able to take over and potentially be root. So if sudo has access to specific file to run as root, you could figure it out exactly what that file does and then take advantage of it.
Okay.
I can show you something else later on if we still have time. I'll let her do her magic, but that's one of those things.
Yeah, let's finish her off.
Okay.
Finish her off. Great job, guys. Okay, let me just bring up one slide here, and you can stop listening to me talk tonight. Okay, so last but not least, I want to thank you guys all for coming out. I hope you walked away with some new knowledge. And I hope that basically what we just learned was simple Python scripting. We know that we don't have to do little Indian anymore. We can use struct and pack, and a low entropy of 32-bit systems. And as you can see, this one I did took way longer. His hit right away. Okay, so we bypassed DEP, we bypassed ASLR, and we took over the full system. If there's any questions, let me know. I am on LinkedIn, I'm on YouTube, I'm on Twitter too much. And reach out to me if you ever guys want to jump in. I do bypassing stack cookies and all this sort of stuff as well on my YouTube. But we just had to compact everything down for tonight's lesson. So I hope you guys enjoyed, and thank you so much for coming out. And I'm going to shut up now. Thank you.